Hello everyone, my name is Veronica and welcome back to the lecture hall. I know it's been a while and we have a new setup. Today we are starting our first video of our abstract algebra course, or our group theory course. We are going to be talking about binary operations and structures. We're first going to get into the notion of what a binary operation is, and then we are going to get into what a full binary structure is. Then we're going to cover the definition, closure, associativity, and commutativity, as well as identities and inverses. A binary operation on a set y is a function that maps two elements from y to another element in y. So for example, plus would be a binary operation in the integers, rationals, reals, and complex. Now we talk about a binary structure. A binary structure is a pair x comma star where x is a set and star is a binary operation. An example of this would be the integers under plus or the real numbers under multiplication. Now onto the notion of closure, and this is really important. So we're going to let x comma star be a binary structure and let S be a subset of x. S is said to be closed under that operation for every x and y in that set S if x star y is still in S. So let's look at an example. We're going to take the integers with addition. It will be closed because we know that for any x and y that we take from the integers, x plus y will be in the integers. For example, 3 plus 4 equals 7. 7 is in the integers. Let's now look at a non-example of closure. Let's take the natural numbers under subtraction. We know it's not going to be closed because we can look at a specific example. Take 4 minus 5, that equals -1. That's not going to be inside of the natural numbers, so it won't be closed. Next, we're looking at the notion of associativity and commutativity. We looked at this in algebra when we do addition and multiplication. So let S be a binary structure. S will be associative if for every A, B, and C in S, A star B star C is going to be equal to A star B star C. So an example of this would be the integers with plus, the real numbers with multiplication, or we could have f under composition where f is a set of functions in the real numbers. Now looking at the definition of commutativity. Let A star be a binary structure. A is said to be commutative if for every x and y inside of A, x star y will equal y star x. So an example would be addition under the integers, rational numbers, real numbers, and complex numbers. And same for multiplication. We know those are commutative. Those are the examples that we saw in our Algebra 1 or maybe Algebra 2 classes. A non-example of commutativity would be matrix multiplication. We learned in our linear algebra class that matrix multiplication is not commutative. Now getting into the last few topics, identity elements and inverse elements. So we let A comma star be a binary structure. E will be the identity element if for every A in A star E is equal to E star A, which is just equal to A. So an example of this would be 0 in the integers under addition, right? Any number plus 0 is that number. Just like how 1 is an identity element for R, the real numbers, under multiplication, because anything times 1 will be itself. Finally, we're going to look at the definition of an inverse element. So, let A star be a binary structure as same before. A has an inverse element if for every A in A, there exists an A prime in A, such that A star A prime will equal A prime star A, which will equal E, which is the identity element. So let's look at an example. The integers under addition will have identity or inverse elements, my apologies, because A plus a negative A is equal to negative A plus A, which equals 0. So we look at the element 3. Well, 3 plus a negative 3 equals 0. So the inverse of 3 would be negative 3 in the integers. That is all I wanted to cover in the video today. New setup. Let me know if there's anything I can do to make it better. Testing out the green screen. Thank you so much for watching. Have a great day.